Look at this image. The pillars of creation. 3 towering columns of cosmic gas and dust, stretching 4 light years into space. They look solid. They look like something you could touch, like giant stone monuments carved by the universe itself. Every space documentary shows them. Every astronomy textbook features them. And if you have ever looked at this image and thought about what it would be like to fly a spacecraft through those clouds, to disappear into that colorful cosmic fog like the Millennium Falcon hiding from star destroyers, I need to tell you something that will fundamentally change how you see these objects. Those pillars would kill you. Not because they are dense, not because they are thick, but because they are almost completely empty. The pillars of creation contain approximately 4,000 particles per cubic centimeter. That sounds like a lot until you compare it to the air you are breathing right now, which contains 25 quintillion particles per cubic centimeter. The pillars are 2.5 quadrillion times thinner than Earth's atmosphere. They are 10,000 times emptier than the best vacuum we have ever created in a laboratory on Earth. If you compressed an entire pillar, the size of our solar system down to the density of air, you would have maybe a few kilograms of material, and yet these near-empty structures would destroy you, your spacecraft, and any hope of survival in ways that are far stranger and more terrifying than science fiction has ever shown us. So why is it impossible to survive inside a nebula? The answer involves vacuum physics, radiation you cannot see, temperatures that do not work the way you think they do, and distances so vast that escape becomes mathematically absurd. But before we can understand how nebulae kill, we need to understand what they actually are, because almost everything you think you know about them is probably wrong. The word nebula comes from the Latin word for cloud or mist. Ancient astronomers used it to describe any fuzzy patch of light in the night sky that was not a star. For centuries, nobody knew what these objects were. Some thought they were distant galaxies. Some thought they were clouds of luminous gas. Some thought they were star systems in the process of forming. The debate was not settled until the 20th century. And even then, the answers turned out to be stranger than anyone expected. Modern astronomers recognize several distinct types of nebulae, and each one presents its own unique nightmare for survival. Emission nebulae are regions where hot young stars blast surrounding gas with ultraviolet radiation so intense that it strips electrons from hydrogen atoms, ionizing the gas and causing it to glow. The Orion Nebula is the most famous example, a stellar nursery located about 1,300 light-years from Earth, where new stars are being born right now. The gas in emission nebulae typically reaches temperatures between 8,000 and 10,000 Kelvin, hot enough to glow with that distinctive reddish-pink color you see in photographs. Reflection nebulae do not generate their own light. Instead, they scatter starlight from nearby stars, the same way Earth's atmosphere scatters sunlight to create blue skies. The dust particles in these nebulae preferentially scatter shorter wavelengths, which is why reflection nebulae often appear blue in photographs. Planetary nebulae have nothing to do with planets. The name is a historical accident from when astronomers thought these round, fuzzy objects might be planetary systems forming. They are actually the death shrouds of sun-like stars, shells of gas expelled during the final stages of stellar evolution. The central stars of planetary nebulae are white dwarfs with surface temperatures reaching 120,000 to 200,000 Kelvin, making them among the hottest objects in the universe. Supernova remnants are the cosmic debris fields left behind when massive stars explode. The Crab Nebula is the most studied example, the remains of a star that exploded in 1054 AD, bright enough to be visible in daylight for 23 days and recorded by Chinese astronomers as a guest star. Supernova remnants expand at thousands of kilometers per second and generate radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, with energies exceeding 100 trillion electron volts. Dark nebulae are clouds of dust and molecular gas so thick that they block light from stars behind them, appearing as black voids against the background glow of the Milky Way. These are the coldest structures in the universe, with temperatures as low as 10 to 20 Kelvin in their cores. The Boomerang Nebula holds the record at just 1 Kelvin, colder than the cosmic microwave background radiation that fills all of space. But here is the critical thing that unites all of these different types of nebula. Despite how different they look, despite the range of temperatures from 1 Kelvin to millions of Kelvin, despite the variety of compositions and origins, they all share one fundamental characteristic. They are all essentially empty. The densest regions of molecular clouds, the places where stars actually form, contain maybe 100,000 to 1 million particles per cubic centimeter. That sounds impressive until you remember that Earth's atmosphere contains 10 to the 19th power particles per cubic centimeter. Even the densest nebula regions are at least 10 trillion times thinner than the air you are breathing. And most nebulae are nowhere near that dense. The glowing regions of emission nebulae typically contain only 100 to 10,000 particles per cubic centimeter. Planetary nebulae average around 1,000 particles per cubic centimeter. Supernova remnants can be even thinner. Paul Scowen is an astronomer at Arizona State University who co-photographed the famous 1995 Hubble image of the pillars of creation. He has spent decades explaining to people what they are actually looking at. The image leads us to believe that the contrast between the pillars and the space between them is large, he explains. The pillars look almost solid. However, the amount of material we are looking through, rather than the density of the gas, determines this contrast. Think about fog. When you look at a fog bank from a distance, it appears solid, like a wall you could walk into. But when you actually enter the fog, it seems to recede in front of you. You never actually reach the solid part, because there is no solid part. The fog is spread out over such a large volume that any individual cubic meter contains almost nothing. Yet the cumulative effect across hundreds of meters creates the illusion of density. Nebulae work the same way, except the distances involved are not hundreds of meters. They are light years. When the Hubble Space Telescope photographs the pillars of creation, it is collecting photons that have traveled through approximately half a light year of gas. That is roughly 4.7 trillion kilometers of material, even though any individual cubic centimeter contains almost nothing. Those trillions upon trillions of cubic centimeters add up to create the appearance of solid structures. But the reality is that a nebula the size of Earth would weigh only a few kilograms. This is where the survival problem begins, because the danger of a nebula is not that you would fly into something solid. The danger is that you are flying through an almost perfect vacuum that happens to glow with radiation from embedded stars. Let me walk you through exactly what would happen to an unprotected human being inside a nebula. The moment you are exposed to nebula conditions, you are exposed to vacuum. Not the partial vacuum of high-altitude aircraft, or even the near vacuum of low Earth orbit. You are exposed to a vacuum billions of times more complete than anything we can create in a laboratory. The pressure inside a nebula is approximately 10 to the negative 13th pascals. For comparison, the threshold at which water boils at body temperature, what aerospace medicine calls the Armstrong line, occurs at about 6,300 pascals. Your body requires a minimum pressure of roughly 47 millimeters of mercury just to keep your blood oxygenated and your tissues from outgassing. Nebulae provide essentially zero pressure. The physics from this point forward are merciless. Within the first 5 seconds, the air in your lungs explosively decompresses. If you make the mistake of holding your breath, your lungs rupture from the pressure differential. Your skin begins to swell as water in your tissues vaporizes through a process called ebullition. Your body expands to roughly twice its normal volume, constrained only by the elasticity of your skin. Contrary to science fiction, you do not explode. Human skin is remarkably strong, but you do inflate like a grotesque balloon. We know these effects are real because of a 1965 accident at NASA's Manned Spacecraft Center in Houston. A technician's spacesuit suffered a rapid decompression during a vacuum chamber test. He remained conscious for about 14 seconds, long enough to feel the saliva on his tongue begin to boil. His last memory before losing consciousness was the sensation of bubbling on his tongue. He survived only because technicians were able to repressurize the chamber within 30 seconds. By 9 to 15 seconds of vacuum exposure, deoxygenated blood reaches your brain and you lose consciousness. According to Federal Aviation Administration guidelines, you have no more than 5 to 10 seconds to take any meaningful action before you are physically incapable of helping yourself. Astronaut Chris Hadfield summarizes it with dark simplicity. 90 seconds, and you are a satellite. The Soyuz 11 tragedy of 1971 remains the only incident in spaceflight history where humans actually died from vacuum exposure in space. 3 Soviet cosmonauts lost their lives when a pressure equalization valve opened prematurely during re-entry preparation. They were found with dark blue patches on their faces, blood in their lungs, and nitrogen bubbles in their circulatory systems. They had no time to react. The decompression took seconds. But here is where nebulae become even more dangerous than ordinary space, because vacuum is just the beginning. The real horrors come from what fills that vacuum. Nebulae are not empty of energy. They are flooded with radiation. Consider the Orion Nebula, the closest massive star-forming region to Earth. At its heart sits a cluster of hot young stars called the trapezium. The brightest of these, Theta 1 Orionis C, has a surface temperature of approximately 39,000 Kelvin and luminosity somewhere between 200,000 and 251,000 times that of our Sun. It produces 3 to 4 times more ionizing ultraviolet radiation than all other trapezium stars combined. Here is what that means in practical terms. Our Sun emits about 0.5% of its energy as ionizing ultraviolet radiation, the kind that can strip electrons from atoms and damage biological tissue. Theta 1. Orion's C emits virtually 100% of its energy as ionizing radiation. It is a searchlight of destruction pointed in all directions simultaneously, and it illuminates the entire Orion Nebula with sterilizing intensity. If you were floating anywhere within the Orion Nebula, that radiation would be bombarding your cells. Without the protection of Earth's atmosphere and magnetic field, without any shielding whatsoever, you would be receiving a lethal dose of radiation within minutes to hours, depending on your distance from the central stars, and you would have no warning. Ultraviolet radiation is invisible. You cannot see it coming. You would simply feel increasingly ill as your DNA shattered and your cells began to die. But the Orion Nebula is mild compared to some other nebulae. The Crab Nebula is the remnant of a supernova that Chinese astronomers recorded in 1054 AD. At its center sits a pulsar, a neutron star only 28 to 30 kilometers in diameter, but containing more mass than our entire sun, spinning 30.2 times per second. This cosmic lighthouse generates synchrotron radiation as electrons spiral through intense magnetic fields at velocities approaching the speed of light. The Crab Nebula is the brightest persistent gamma ray source in the sky, above 30 kilo-electron volts. It emits radiation at energies exceeding 100 trillion electron volts, making it the first cosmic source ever detected at such extreme energies. Astronomers actually use the Crab as a calibration standard for X-ray telescopes, with a unit called the millicrab, measuring the brightness of other X-ray sources relative to it. The central pulsar pumps approximately 10 to the 38th ergs per second into the surrounding nebula, equivalent to 75,000 to 148,000 times the luminosity of our sun. And virtually all of that energy is high-energy radiation. Gamma rays, X-rays, relativistic particles. A spacecraft passing through the Crab Nebula would be bathed in radiation that would fry its electronics, corrupt its computer memory, and irradiate its occupants with doses measured in hundreds or thousands of sieverts. The lethal dose for humans is roughly 5 sieverts, and the Crab is just one supernova remnant. The galaxy contains hundreds of them, and supernova remnants are known to be cosmic ray factories, accelerating particles to energies up to 10 to the 14th electron volts per nucleon. These are the highest energy particles found in nature, capable of passing through meters of solid lead. But wait, what about the cold nebulae? The dark molecular clouds where temperatures drop to just 10 or 20 Kelvin. Surely those would be safer. This is where the physics of heat transfer becomes counterintuitive. Temperature measures the average kinetic energy of particles, how fast they are moving. A gas at 10,000 Kelvin contains particles zipping around at tremendous speeds. But heat transfer requires those particles to actually collide with you. And in a nebula with only 1,000 particles per cubic centimeter compared to 10 to the 19th in breathable air, collisions are extraordinarily rare. You would not burn in a 10,000 Kelvin nebula. There simply are not enough particles hitting you to transfer meaningful amounts of heat. The total thermal energy reaching your body per second would be negligible. Instead, you would freeze. Your body radiates heat as infrared photons. On Earth, the surrounding air absorbs some of that radiation and re-radiates it back, creating equilibrium. In a nebula, your infrared photons sail off into the void with nothing to return them. You are a 310 Kelvin object radiating into a universe whose average temperature is just 3 Kelvin. The cosmic microwave background, the Stefan Boltzmann law, governs this radiative heat loss. A human body with approximately 2 square meters of surface area radiating into a 3 Kelvin environment loses heat at a rate of roughly 1,000 watts. That is like sitting naked in front of an extremely powerful air conditioner. Your core temperature would drop progressively, leading to hypothermia and death over a period of hours. In the coldest nebulae, like the Boomerang Nebula at just 1 Kelvin, this process would be even faster. The temperature differential between your body and your environment would be over 300 degrees, driving rapid heat loss through radiation alone. But none of this matters if you cannot escape in the first place. And this is where nebulae reveal their cruelest trick. They are incomprehensibly large. The Orion Nebula spans approximately 24 light-years in diameter. The Carina Nebula stretches 300 to 460 light-years across. Even the pillars of creation, which look like small features within the larger Eagle Nebula, are 4 light-years tall. That is roughly the distance from our Sun to Alpha Centauri, our nearest neighboring star system. Voyager 1 is currently the fastest object humanity has ever sent into interstellar space, traveling at about 17 kilometers per second. At that speed, crossing 1 light-year takes approximately 17,500 years. Traversing the Orion Nebula would require roughly 440,000 years. The Carina Nebula? About 8 million years, even if you survived the vacuum. Even if you somehow shielded yourself from the radiation, even if you solved the heat loss problem, you would die of old age billions of times over before reaching the other side of a major nebula. And the nebulae do not care. They are not waiting for you to escape. They are changing while you travel. The pillars of creation are being destroyed right now. Ultraviolet radiation from the hot young stars in the Eagle Nebula is evaporating them at a rate that will completely dissolve the pillars in approximately 3 million years. Some astronomers have even suggested that a supernova shockwave may have already destroyed them about 6,000 years ago, and we simply have not seen the destruction yet because the light from that event has not reached us. Supernova remnants, like the Crab Nebula, are expanding at 1,500 kilometers per second. The environment you enter would be substantially different from the environment you exit, if you could ever exit at all. And this raises a question that science fiction has never adequately addressed. What would it actually look like from inside a nebula? Would you see those gorgeous colors swirling around you like cosmic fog? Probably not. Phil Platt is an astronomer who writes about common misconceptions regarding space. He has addressed this question directly. Perhaps the most surprising thing of all about a nebula is that if you were inside it, counterintuitively, you might not see it at all. All that nebulosity and color are obvious through a telescope. But if you were inside the nebula, that light would be spread out all over the sky. That substantially dims it, making it difficult to see. The European Southern Observatory uses an analogy that cuts through the misconception. These clouds are like a very, very thin fog. From a few meters away, fog seems like a cloudy wall that you will walk into. But as you move closer, the fog seems to disappear. it always seems to stay just out of reach. And these clouds are much less thick than fog. Here is the proof that you would notice nothing unusual. Earth is currently inside a nebula right now. We are sitting within something called the local bubble, a cavity approximately 1,000 light-years across, carved out by roughly 15 supernovae over the past 10 to 20 million years. The local bubble has a density of about 0.05 atoms per cubic centimeter, 1/10 the average density of interstellar space. We have been inside this structure for approximately 5 million years, and humanity had absolutely no idea until careful measurements in the 1970s and 80s revealed its presence. For all of human history, we have lived inside a nebula and never noticed. This is what makes science fiction depictions so frustrating to astronomers. Every space opera shows nebulae as thick, colorful fog banks where ships can hide from sensors and sneak up on enemies. Star Trek too. The Wrath of Khan features the Mutara Nebula, where the Enterprise and Reliant play cat and mouse in what looks like a giant thundercloud. Star Wars has the Kessel Run, threading through the Akkadi's maelstrom. Countless video games use nebulae as atmospheric backdrops or tactical obstacles. The European Southern Observatory was so exasperated by these depictions that they titled an educational article, quote, "Why you could not hide your spaceship in a nebula," end quote. The answer, of course, is that there is nothing to hide in. The gas is too thin to block sensors. The colors are too dim to see with the naked eye. The dramatic visual effects exist only in long exposure photographs taken by space telescopes over periods of hours. Phil Plett gives Star Trek 2 credit for getting the colors roughly correct, but notes the fundamental physics problem. That would not really happen because the nebula does not have a sharp enough edge. Even at sublight speeds the Enterprise was traveling, it would take several minutes or really hours to feel any real deceleration due to drag. Nebulae just sort of fade away with distance, getting thinner and less dense. In many cases, this happens over many billions or tens of billions of kilometers. There is no wall to fly through. There is no fog to disappear into. There is just a gradual transition from slightly less empty to slightly more empty, spread across distances measured in light years. But let me tell you about something even stranger, something that confused astronomers for over 60 years and reveals just how alien nebular conditions really are. In 1864, the English astronomer William Huggins pointed his telescope at the Cat's Eye Nebula and examined its light through a spectroscope. He was expecting to see the absorption lines characteristic of sunlight reflected off a distant gas cloud. Instead, he saw bright emission lines indicating the nebula was generating its own light. More puzzling, some of those emission lines did not match any known element. The brightest line glowed at a wavelength of 500.7 nanometers, a distinctive green color that appeared in nebula after nebula, but never in any laboratory on Earth. Astronomers concluded they had discovered a new element. They called it nebullium. For 63 years, nebullium remained one of astronomy's great mysteries. The periodic table was filling up with new elements discovered through spectroscopy, so a new element seemed plausible. But nobody could find nebullium on Earth. Nobody could determine its atomic weight or chemical properties. It existed only in the ghostly light of distant nebulae. In 1927, American physicist Ira Sprague Bowen finally solved the mystery. Nebulae did not exist. The mysterious green lines came from ordinary oxygen, but oxygen in conditions that were physically impossible to create on Earth. The technical name is forbidden line emission. Certain quantum mechanical transitions in atoms are not forbidden in the sense of being physically impossible. They are forbidden in the sense of being incredibly unlikely, roughly 100 million times less likely than normal transitions. Under laboratory conditions, atoms constantly collide with other atoms, knocking electrons out of metastable energy states before these unlikely transitions can occur. The forbidden lines never have a chance to appear, but in the extreme vacuum of a nebula, atoms drift for 10 seconds to 10,000 seconds between collisions. In that cosmic solitude, electrons can finally complete their forbidden transitions, emitting photons at wavelengths that simply cannot exist under terrestrial conditions. These forbidden lines can account for 90% or more of a planetary nebula's visible light. When you look at a photograph of a nebula and see that characteristic green glow, you are seeing light that is literally impossible to create on Earth. You are seeing the signature of a vacuum so perfect, a density so impossibly low, that the normal rules of atomic physics bend in ways that took 6 decades to understand. This is what makes nebulae so haunting. They are not just empty. They are empty in ways that reveal new physics. They are laboratories of impossible conditions, stretching across light years, glowing with light that should not exist. And we have not even discussed what happens when stars are being born inside them. Young stellar objects are violent. As protostars form from collapsing clouds of gas and dust, they spin up and generate powerful magnetic fields. Excess material falls onto the protostar's surface in accretion events that can increase the star's brightness by factors of hundreds. And along the rotation axis, the protostar launches bipolar jets of ionized plasma at velocities of 100 to over 1,000 kilometers per second. These jets are called Herbig-Haro objects, named after the astronomers George Herbig and Guillermo Haro, who identified them in the 1940s and 50s. When the jets collide with surrounding interstellar medium, they create bow shocks, visible as glowing knots of emission. Some Herbig-Haro objects feature jets that stretch 8 light-years or more from their parent star, moving so fast that their motion is visible in photographs taken years apart. The James Webb Space Telescope has captured stunning images of Herbig-Haro 211, where a protostar drives jets at 80 to 100 kilometers per second through surrounding molecular gas. The jets create shock fronts that heat gas to thousands of degrees. Any spacecraft passing through such a jet would be sandblasted by high-velocity ionized particles, battered by shock waves, and irradiated by the emission from collisional heating. And these jets are unpredictable. Protostars experience accretion outbursts that can increase jet activity dramatically. The region around a forming star is dynamic, violent, and utterly hostile to anything not made of rock or plasma. Then there is the Carina Nebula, home to one of the most unstable stellar systems known. Eta Carinae is a binary star system located about 7,500 light-years from Earth. The primary star has between 90 and 150 times the mass of our Sun. The secondary has between 30 and 80 solar masses. The primary is what astronomers call a luminous blue variable, one of the rarest stellar classifications, a massive star in a phase of extreme instability with a luminosity 4 to 5 million times that of our Sun. Between 1837 and 1858, Eta Carinae underwent what astronomers call the Great Eruption. The star briefly became the second brightest star in the sky, visible from the southern hemisphere as a brilliant point of light. It ejected between 10 and 40 solar masses of material at velocities reaching 3,000 kilometers per second, creating the bipolar homunculus nebula that surrounds the system today. Here is what makes Eta Carinae terrifying. The collision zone, where the stellar winds from the two stars meet, reaches temperatures of approximately 100 million Kelvin. That is almost 7 times hotter than the core of our Sun. This region is detectable only in X-rays, a screaming hot plasma generated by two stars literally slamming their atmospheres together at thousands of kilometers per second. Eta Carinae is expected to explode as a supernova within the next several thousand to few million years. When it does, it will release more energy in seconds than our Sun will emit in its entire 10 billion year lifetime. Any spacecraft within the Carina Nebula at that moment would be vaporized by the flash. But even now, even before the explosion, the Carina Nebula is one of the most hostile environments in our region of the galaxy. The James Webb Space Telescope's famous cosmic cliffs image shows the edge of a gaseous cavity in the northwest portion of the nebula. Mountains of gas up to 7 light-years tall, being eroded by radiation from hot young stars. Hundreds of previously hidden protostars with planet-forming disks were revealed in that single image, each one a source of jets and outflows and radiation. The Carina Nebula is not a peaceful stellar nursery. It is a war zone where stars are being born and destroyed simultaneously, where radiation pressure sculpts gas into towering pillars only to dissolve them over millions of years, where the most massive stars burn through their fuel in cosmic eye blinks before exploding and seeding the next generation of stellar formation. This is the reality behind those beautiful photographs. Not peaceful clouds drifting through space, not gentle mists of cosmic gas, but violent, radiation-flooded voids where the fundamental conditions of existence are hostile to any form of biological life. Let me put this in perspective with one final thought experiment. Imagine you are an astronaut on a spacecraft approaching the Orion Nebula. Your ship is equipped with perfect radiation shielding, perfect vacuum protection, unlimited fuel, and propulsion that can maintain 1/10 the speed of light indefinitely. You are as protected as technology can make you. At 1/10 light speed, crossing the 24 light-year diameter of the Orion Nebula takes 240 years. Your spacecraft's life support systems, its computers, its structural materials must all function flawlessly for almost 2.5 centuries. Any failure means death. Any malfunction in systems designed to operate for decades at most becomes lethal when stretched across centuries. And during that entire transit, you are passing through a radiation environment that makes interplanetary space look benign. The trapezium's ultraviolet output, energetic particles from stellar winds, X-rays from shock-heated gas. Your shielding is handling loads far beyond what any real spacecraft has ever encountered, for far longer than any space mission has ever lasted. Even if your ship survives, even if your life support holds, Even if you personally survive through some form of suspended animation or generation ship, you emerge from the other side of the Orion Nebula into what? More empty space, more cosmic wilderness, more light years of nothing between you and any possible destination. The Orion Nebula is not on the way to anywhere. There is no shortcut through it, no advantage to be gained by transit. It is simply there, a beautiful, glowing obstacle that would kill you if you tried to cross it, and would take centuries, even if it could not. This is why survival inside a nebula is impossible. Not because of any single lethal factor, though there are many, but because of the combination of vacuum, radiation, temperature, distance, and time that creates a gauntlet no spacecraft could run and no human could survive. The photographs lie to us. They show solid-looking pillars and colorful clouds and dramatic vistas because they accumulate light across distances and time spans that dwarf human experience. They flatten four-dimensional structures onto two-dimensional images and compress hours of exposure into single frames that our eyes can process. But the reality is that nebulae are voids that glow. They are absences filled with energy. They are the closest thing the universe has to beautiful death, painted across light years in colors generated by physics that cannot exist on Earth. We can study them through telescopes. We can photograph them with space observatories. We can analyze their spectra and model their physics and trace the life cycles of stars being born and dying within them. But we cannot visit them. We cannot touch them. We cannot survive inside them. And perhaps that is fitting. Perhaps some things should remain forever beyond our reach, visible but inaccessible, beautiful but deadly. The universe is not built for human comfort. It is built on scales and extremes that existed for billions of years before we evolved and will persist for trillions of years after we are gone. Nebulae remind us of this. They remind us that the cosmos does not care about our fragility. They remind us that beauty and lethality can coexist in the same object, that something can inspire awe and kill us simultaneously. The next time you see an image of the pillars of creation, or the Orion Nebula, or the Carina Nebula, remember what you are actually looking at. Not a cloud, not a fog, not anything solid or safe or hospitable. You are looking at a near-perfect vacuum flooded with radiation, spanning distances that would take millennia to cross, filled with light generated by physics that should be impossible, slowly destroying itself even as new stars ignite within its depths. You are looking at one of the most hostile environments in the known universe, wrapped in colors that take your breath away. And that contrast, that impossible combination of beauty and death, might be the most profound thing the universe has to teach us. We are small. We are fragile. We exist in a tiny bubble of habitability on a single rocky planet, orbiting an ordinary star in the suburbs of an average galaxy. Everything beyond that bubble, including the gorgeous nebulae that decorate our night sky, would kill us without hesitation and without malice. The universe is not malevolent. It is simply indifferent. And nebulae are monuments to that indifference, cathedrals of emptiness, where the rules that govern our lives simply do not apply. Can you survive inside a nebula? No. Would you even know you were inside one? Probably not. Would it kill you anyway? Absolutely. And that is perhaps the strangest thing of all. The most dramatic looking objects in the cosmos would destroy you through the most mundane of mechanisms, not through exotic physics or alien dangers or anything you could not find in ordinary interplanetary space. Just vacuum, just radiation, just cold, just distance. The same things that make space hostile everywhere make nebulae doubly hostile. The same physics that would kill you outside a nebula would kill you faster inside one. The beauty adds nothing but irony. So look at those photographs. Marvel at the colors. Wonder at the scale. But remember that you are looking at a graveyard for anything made of flesh and blood. You are looking at conditions so extreme that they generate light through forbidden quantum transitions. You are looking at the death of stars and the birth of stars and the empty spaces between where nothing lives and nothing can live. That is what a nebula really is. And that is why, despite everything science fiction has shown us, surviving inside one will always be impossible. But I want to take you deeper into this because we have talked about nebulae in general terms, and I think you deserve to understand specific examples. Let me walk you through 5 famous nebulae and show you exactly what would kill you in each one. The Orion Nebula, Messier 42, the closest massive star-forming region to Earth at 1,344 light-years, give or take 20. When you look at the constellation Orion on a winter night, that fuzzy patch in the sword is this nebula, visible to the naked eye as a smudge of light even from moderately light, polluted locations. The Orion Nebula spans roughly 24 light-years across. Its ionized gas reaches temperatures between 8,000 and 10,000 Kelvin. At its heart sits the trapezium cluster, 4 hot young stars that power the entire nebula's glow. Theta 1, Orionis C, the brightest and hottest of these, has a surface temperature around 39,000 Kelvin and is the most luminous star visible to the naked eye when measured in ionizing ultraviolet radiation. But here is what makes the Orion Nebula particularly interesting for our survival thought experiment. It contains what astronomers call supersonic bullets. These are knots of gas roughly 10 times the diameter of Pluto's orbit, tipped with glowing iron atoms, traveling at velocities between 10 and 50 kilometers per second relative to surrounding material. The bullets were ejected during violent events in the nebula's star-forming history, and they are still plowing through the gas, leaving glowing wakes of shocked material behind them. Imagine you are floating in the Orion Nebula. The vacuum is killing you. The radiation from the trapezium is killing you. And somewhere out there, unseen until it is too late, one of these supersonic bullets is tearing through the nebula at 50 kilometers per second. Even at nebula densities, impact with such a structure would be catastrophic. Not that you would live long enough to encounter one. The Orion Nebula is also incredibly young by cosmic standards, only about 1 to 3 million years old. Stars are still forming within it right now. Protoplanetary disks surround young stellar objects, the raw material for planets condensing even as the nebula slowly disperses. It is a construction zone on the cosmic scale, full of activity and energy and violence. Nicolas Claude Fabry de Peiresc first observed the Orion Nebula through a telescope in 1610, the same year Galileo was discovering the moons of Jupiter. Charles Messier catalogued it as M42 on March 4th, 1769. William Huggins proved it was luminous gas through spectroscopy in 1865, resolving decades of debate about whether nebulae were composed of gas or unresolved stars. For over 400 years, humans have studied this object. For 400 years, it has been completely beyond our reach, and it will remain so forever. The Eagle Nebula and the Pillars of Creation deserve special attention because they are probably the most famous astronomical image ever taken. When Hubble captured the pillars in April 1995, the image became iconic almost overnight. It appeared on magazine covers, in textbooks, on postage stamps. It became shorthand for the majesty of the cosmos. The Eagle Nebula itself lies about 5,700 to 7,000 light-years from Earth and spans roughly 70 by 55 light-years in total. The pillars are just one small feature within this larger structure, but they are spectacular. The tallest pillar stretches approximately 4 light-years from base to tip. That is about 23 trillion miles. You could fit the entire distance from the Sun to Alpha Centauri within a single pillar. Within those pillars, astronomers have identified small, dense regions called evaporating gaseous globules, or EGGs. 73 of these EGGs have been catalogued in the Pillars region. 11 of them contain infant stellar objects. 4 are massive enough that they will definitely become stars. You are looking at star formation caught in the act, but the pillars are doomed. The same ultraviolet radiation that makes them visible is also destroying them. Hot young stars in the Eagle Nebula are evaporating the outer layers of the pillars at a rate that will completely dissolve them in approximately 3 million years. A 2015 study using the European Southern Observatory's Very Large Telescope determined the evaporation rate with enough precision to make this prediction. And here is the twist. Some astronomers have suggested that a supernova exploded near the pillars about 6,000 years ago. If so, the shockwave would have already destroyed them. But because the Eagle Nebula is about 7,000 light-years away, the light from that destruction has not reached us yet. We might be looking at a ghost, an image of something that no longer exists, preserved only because information cannot travel faster than light. When you look at the pillars of creation, you might be looking at the past tense. The structures in the photograph may have been demolished 6,000 years ago, and the evidence of their destruction is still en route to Earth, traveling at 300,000 kilometers per second, but still not fast enough to catch up with the image we see today. The James Webb Space Telescope photographed the pillars again in October 2022, revealing them in infrared light for the first time at high resolution. The JWST images show the pillars as semi-transparent, with hundreds of previously hidden young stars visible through and around the dusty columns. The pillars look different at different wavelengths, more ghostly in infrared, more solid in visible light, a reminder that what we see depends entirely on how we choose to look. The Crab Nebula is a different kind of beast entirely. While the Orion Nebula and Eagle Nebula are star-forming regions, places where new stars are being born, the Crab is a tomb. It is what remains when a massive star dies. On July 4th, 1054 AD, Chinese astronomers recorded the appearance of a guest star in the constellation we now call Taurus. The star was so bright, it was visible in daylight for 23 days. It remained visible to the naked eye at night for approximately 2 years before fading from view. Arabic and Japanese records also mention the event. A possible Anasazi pictograph at Chaco Canyon in New Mexico shows a crescent moon beside a bright star, which some researchers interpret as a record of the supernova. What those ancient observers witnessed was the death of a star roughly 10 times more massive than our Sun. The star had exhausted its nuclear fuel, its core collapsing in a fraction of a second, triggering a rebound explosion that blew its outer layers into space at thousands of kilometers per second. For a few weeks, that single dying star outshone entire galaxies. What remains is the Crab Nebula, a tangle of glowing filaments approximately 11 light-years across, still expanding at 1,500 kilometers per second, nearly 1,000 years after the explosion. At its center sits the Crab Pulsar, a neutron star only about 28 kilometers in diameter, but containing 1.4 to 2 solar masses, more than the mass of our Sun compressed into a sphere the size of a city. The pulsar spins 30.2 times per second. Every rotation, it sweeps a beam of radiation across our line of sight like a cosmic lighthouse. That radiation spans the entire electromagnetic spectrum, from radio waves to gamma rays. The pulsar is gradually slowing down as it radiates energy, and that energy pumps into the surrounding nebula, keeping it glowing nearly a millennium after the explosion that created it. I mentioned earlier that the Crab is the brightest persistent gamma ray source in the sky above 30 kilo-electron volts. Let me put some numbers on that. The Crab has been detected emitting gamma rays at energies exceeding 100 tera-electron volts. For comparison, the Large Hadron Collider, the most powerful particle accelerator ever built, achieves collision energies of about 13 tera-electron volts. The Crab pulsar is accelerating particles to energies almost 10 times higher than anything humans have ever achieved in a laboratory. In 2019, the MAGIC telescope system detected gamma-ray photons from the Crab Nebula with energies up to 1.5 tera-electron volts. Earlier that year, the Tibet Air Shower Array detected photons exceeding 100 tera-electron volts. These are the highest energy photons ever detected from a cosmic source. If you flew a spacecraft into the Crab Nebula, you would be entering a particle accelerator. Electrons are spiraling through intense magnetic fields at velocities approaching the speed of light. Gamma rays are penetrating everything in their path. The central pulsar is pumping energy into the nebula at a rate equivalent to over 100,000 suns. Your radiation shielding would be overwhelmed within minutes or hours, depending on distance from the pulsar, and the nebula is still evolving. Hubble observations from 1995 to 2000 revealed visible changes in the inner nebula on timescales of days. Wisps of glowing material appear and disappear as the pulsar wind creates and destroys structures faster than any other observed nebula. The Crab is alive in a way that most nebulae are not, a dynamic roiling cauldron of energy and radiation. The Helix Nebula shows us what happens to stars like our Sun when they die. While the Crab is the remnant of a massive star that exploded, the Helix is the remnant of a medium-mass star that simply ran out of fuel and shed its outer layers. Located about 655 light-years from Earth, the Helix is the closest prominent planetary nebula to our solar system. It spans approximately 2.5 to 5 light-years, depending on which structures you measure, appearing in the sky about half the apparent diameter of the full moon. Through a telescope, it looks like a giant eye staring back at you, which is why it is sometimes called the Eye of God. The central star of the helix is a white dwarf designated WD2226-210. Its surface temperature is approximately 120,000 Kelvin, making it among the hottest stellar objects known. The star began its life with roughly 6.5 times the mass of our Sun. But through billions of years of evolution and the expulsion of its outer layers, what remains is a stellar corpse with only about 0.6 solar masses compressed into a radius of roughly 17,000 kilometers, comparable to Earth. The gas shells expelled by the dying star are still expanding outward at 31 to 40 kilometers per second. Temperature gradients across the nebula are dramatic. The central white dwarf burns at 120,000 Kelvin. Inner knots of gas register around 1800 Kelvin. Outer regions drop to just 900 Kelvin. The nebula formed approximately 10,600 years ago, based on its current size and expansion rate. Most of the energy emitted by the central white dwarf is ultraviolet radiation, invisible to human eyes, but incredibly destructive to biological tissue. If you floated near the center of the Helix Nebula, you would be bathed in UV radiation from a source hundreds of times more luminous than our Sun, compressed mostly into wavelengths that would shatter DNA and sterilize everything they touched. The helix also shows us our future. In about 5 billion years, our Sun will exhaust its hydrogen fuel, expand into a red giant, and eventually shed its outer layers to form a planetary nebula. The Sun will become a white dwarf at the center of an expanding shell of gas, glowing with the last heat of its former glory. Any observers in distant star systems might photograph our solar system's remains the way we photograph the helix today. The Carina Nebula is perhaps the most dangerous nebula we have discussed, and that is saying something. Located about 7,500 light-years from Earth, the Carina Nebula spans 300 to 460 light-years across, making it one of the largest nebulae in the Milky Way. It contains several massive star clusters, multiple regions of active star formation, and some of the most luminous and unstable stars known. I already mentioned Eta Carinae, the binary system at the nebula's heart. But let me give you more detail on just how extreme this object is. The primary star in the Eta Carinae system is a luminous blue variable. This is a class of stars so rare that only a few dozen are known in our entire galaxy. Luminous blue variables are massive stars in a phase of extreme instability, prone to eruptions that can eject significant fractions of their total mass into space. The primary star has between 90 and 150 times the mass of our Sun, and a luminosity 4 to 5 million times greater. During the Great Eruption of 1837 to 1858, Eta Carinae briefly became the second brightest star in the sky, despite being nearly 8,000 light-years away. It ejected between 10 and 40 solar masses of material in twin lobes that now form the Homunculus Nebula, a small bipolar structure embedded within the larger Carina Nebula. The material in the homunculus is still traveling outward at up to 650 kilometers per second. The mass loss rate from Eta Carinae is approximately 1,000th of a solar mass per year. That means the star is shedding about 330 Earth masses worth of material every single year. This material forms a powerful stellar wind traveling at 3,000 kilometers per second. Where this wind collides with the stellar wind from the companion star, temperatures reach 100 million Kelvin. 100 million Kelvin. That is nearly 7 times hotter than the core of our Sun, generated not by nuclear fusion, but by the collision of two stellar winds. This zone is detectable only in X-rays, a screaming hot plasma created by stars literally ramming their atmospheres together. Eta Carinae is a supernova waiting to happen. Astronomers expect it to explode within the next several thousand to few million years. When it does, it will be one of the most energetic events in the recent history of our galaxy. From Earth, the supernova will be visible in daylight, potentially bright enough to read by at night. The gamma ray burst that might accompany the explosion could be dangerous to any planets within a few hundred light years. But the Carina Nebula is dangerous even without the supernova. The James Webb Space Telescope's cosmic cliffs image shows the edge of a gaseous cavity in the nebula's northwest region, sculpted by radiation and stellar winds from hot young stars. The cliffs rise to heights of 7 light years, dwarfing the pillars of creation. Hundreds of young stars with protoplanetary disks are visible in the image, surrounded by jets and outflows and all the violence of active star formation. This is not a peaceful place. It is a cosmic battlefield where stars are being born in violence, and some of them will die in violence, where radiation sculpts gas into towering structures only to tear them apart, where the most massive stars burn through their fuel in mere millions of years before exploding and seeding the next generation. If you flew a spacecraft into the Carina Nebula, you would be entering one of the most energetic environments in the local region of the galaxy. Radiation from dozens of hot young stars, stellar winds at thousands of kilometers per second, the looming presence of Eta Carinae, a star so unstable that astronomers monitor it constantly for signs of imminent explosion. And the distances, always the distances. 300 light years at minimum, at 1/10 light speed, 3,000 years to cross, at Voyager speeds, over 5 million years. These are the realities that science fiction ignores, not because filmmakers do not know better, but because the truth is too hostile and too boring simultaneously. Too hostile because nothing survives. Too boring because nothing happens on human timescales. You cannot tell a story about characters dying of vacuum exposure within 15 seconds. You cannot build dramatic tension around a journey that takes longer than recorded human history. So science fiction gives us colorful fog banks and tactical hiding places and dramatic maneuvers through swirling clouds. And we accept these fictions because they are beautiful and because we want to believe that the cosmos might be navigable, that human ingenuity could overcome any obstacle, that the stars are within our reach. But nebulae teach us otherwise. They teach us that some parts of the universe are simply off limits, not because of technology we have not invented yet, not because of obstacles we could overcome with enough resources or determination, but because the fundamental physics make survival impossible across the timescales and distances involved. We are creatures of atmosphere and warmth, evolved on a planet where the nearest vacuum is hundreds of kilometers away, and the nearest lethal radiation is filtered by a magnetic field and an ozone layer. We experience time in heartbeats and breaths and days, not in the millions of years it takes light to cross a nebula. Nebulae exist on scales that are simply incompatible with human existence. And there is something profound in accepting that, something humbling in recognizing that the universe contains wonders we can see but never touch, beauty we can photograph but never visit. The next time you see an image of a nebula, any nebula, I want you to remember 3 things. First, remember that it is emptier than empty. Whatever solidity the image suggests is an illusion created by accumulated light across distances measured in light years. You could not hide in it. You could not fly through it like fog. You would not even see it if you were inside it. Second, remember that it is flooded with energy, ultraviolet radiation from hot stars, X-rays from shock-heated gas, gamma rays from pulsars, and particle acceleration. The colors that make nebulae beautiful are created by energy that would destroy any unprotected observer. Third, remember the scale. Even the smallest nebulae span light years. Even at impossible speeds, crossing them takes centuries. The distances involved are not obstacles to be overcome, but boundaries that define the limits of what physical travel can achieve. These 3 truths combine to make nebula survival impossible. Not improbable, not difficult, impossible. No amount of technology can change the fundamental physics. No amount of shielding can protect you forever. No amount of fuel can compress the transit time to human lifespans. And I think there is something valuable in understanding this. In an age when we are surrounded by optimistic visions of interstellar travel and space colonization, nebulae stand as reminders that the cosmos has hard limits. Some of those limits might be breakable with future technology. Some of them cannot be broken at all. Knowing the difference matters. It shapes our expectations about what space exploration can achieve and what lies forever beyond our reach. It teaches us to appreciate what we have, this thin shell of atmosphere on this small rocky world, instead of assuming we can always expand outward when we need more room. The universe gave us nebulae. It filled them with impossible light generated by forbidden physics. It stretched them across light years of lethal vacuum, and it placed them far enough away that we can see them in all their terrible glory without being destroyed by their presence. But there is one more thing I want you to understand, because even beyond the vacuum, beyond the radiation, beyond the temperature extremes and the impossible distances, there is something fundamentally strange about nebulae that makes them hostile in ways we rarely consider. The physics inside a nebula do not work the way physics works on Earth. I mentioned earlier the forbidden line emission, the light generated by quantum transitions that cannot occur under laboratory conditions. This is not a minor detail. This is evidence that nebulae exist in a regime of physics so different from our everyday experience that atoms behave in ways that took decades to understand. On Earth, when atoms gain energy, they release it almost instantly through allowed quantum transitions. Electrons jump to higher energy levels and fall back down within nanoseconds or microseconds, emitting photons in the process. The whole cycle happens faster than you can blink. In a nebula, atoms drift in such perfect isolation that they can remain in excited states for seconds, minutes, or even hours. An electron jumps to a higher energy level and then just waits. There is nothing nearby to disturb it. No collisions, no interactions, just emptiness so complete that the normal rules of atomic physics become suspended. When those electrons finally do transition back to lower energy states, they emit photons at wavelengths that are impossible to create in any Earth-based laboratory. The green glow that William Huggins mistook for a new element called nebullium is actually just oxygen. Doing something oxygen cannot do anywhere else in the universe except in the vacuum of interstellar clouds. Think about what this means. You are looking at light that should not exist. Light generated by physics that operates only under conditions so extreme that we cannot replicate them with any technology we possess. The colors in nebula photographs are literally impossible colors, wavelengths of light that nature permits only in environments so hostile that nothing organic could survive to see them. This is why nebulae are so beautiful and so deadly simultaneously. They exist in a realm of physics that requires conditions incompatible with life. The very thing that makes them glow is the thing that makes them uninhabitable. And here is the cruel irony. We are made of materials that came from nebulae. The iron in your blood was forged in the core of a massive star that exploded as a supernova, scattering heavy elements into space where they eventually condensed into planets. The calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every organic molecule in your body, all of it was cooked in stellar furnaces and scattered by stellar explosions. You are nebula material. Literally, the atoms in your body pass through structures like the Crab Nebula or the Carina Nebula billions of years ago. You are star stuff, as Carl Sagan famously said, and that star stuff began its journey through the cosmos in environments exactly like the ones we have been discussing. But you cannot go back. The conditions that created you cannot sustain you. The nebulae that seeded your existence with heavy elements would kill you in seconds if you tried to visit them. It is like a butterfly trying to return to the furnace that forged the iron in its wing muscles. The connection is real. The journey is impossible. This is what makes nebulae so philosophically interesting. They are our birthplace and our cemetery simultaneously. They are where stars live, and where stars die, and where new stars are born from the ashes of the old. They are the life cycle of the cosmos made visible, generation after stellar generation playing out across millions of years. And we stand outside that cycle, looking in through telescopes, trying to understand processes that operate on timescales longer than our species has existed. We photograph nebulae and study nebulae and name nebulae, but we cannot participate in them. We are observers only, separated from these cosmic cathedrals by physics that does not negotiate. There is something almost religious about that separation, something that echoes the old idea of sacred spaces, places humans can approach but cannot enter, can reverence but cannot touch. The universe has its holy of holies, its inner sanctums, and nebulae are among them. We peer through the veil and see glory, but the veil remains. Perhaps that is why nebula images move us so deeply. They are not just beautiful. They are beautiful and forbidden. They represent something we can never have, places we can never go, experiences we can never share. And there is a special poignancy in wanting something impossible. We will continue to photograph nebulae. The James Webb Space Telescope is revolutionizing our view of these structures, revealing details invisible to earlier instruments. The next generation of space telescopes will push even further. We will learn more about how stars form and how they die. We will trace the chemical evolution of the cosmos. We will watch nebulae change over decades and centuries of observation. But we will never visit, never touch, never stand inside one of these glowing clouds and look up at the stars being born around us. The photos will always be remote. The experience will always be second-hand. The beauty will always be at a distance. Perhaps that is enough. Perhaps beauty at a distance is its own reward. Perhaps the proper response to a nebula is not to dream of visiting, but to marvel that such things exist at all. You cannot survive inside a nebula. Nothing can. And the cosmos is more magnificent for containing places so utterly hostile to everything we are. Look up tonight, if you can see the stars. Find Orion. Find that fuzzy patch in the sword, and know that you are looking at something beautiful and deadly and forever beyond your reach. That is the universe we live in. That is the reality behind the photographs. And that is why it is impossible to survive inside a nebula. The universe built these structures without us in mind. It filled them with wonders we can barely comprehend and dangers we cannot survive. It made them beautiful beyond description and deadly beyond imagination. And then it showed them to us anyway. These cathedrals of emptiness, these temples of impossible light, these monuments to scales of time and space that dwarf everything we are. We look, we learn, we marvel, and we remember that some doors are meant to stay closed. The nebulae will be there long after we are gone, glowing, evolving, creating stars and destroying them, painting the sky with colors that should not exist. And perhaps that is the point. Perhaps the lesson of nebulae is that the universe does not need us to be magnificent. It simply is, and we are lucky enough to see it from the one tiny place where looking does not kill us. That is the gift. That is the miracle. That is why we keep looking up.